Hello and welcome back to Calculus, the series where we explore integrals. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Now, please recall from the last video, I introduced the concept of integration, which was divided into two categories: definite and indefinite integration. The first is used to find areas under curves, while the latter is used to find the antiderivative of a function. So today, we will be looking at the basic rules of integration and some basic examples. Once again, please recall from the last video, I introduced the power rule for integration. If we're trying to compute the integral of a function in the form of x to the power of n, where n is simply a real number, the antiderivative of the integral we get is going to be x to the power of n plus 1 divided by the power of n plus 1 and plus c at the end. Next, when computing the integral of the function k times x to the power of n, in this case, the k is simply a coefficient. Just like the derivatives, we can take the k outside and just separately compute the integral of x to the power of n, and then attach the x in the end after we have the antiderivative function. Now, if we are computing the integral of a polynomial in the form of an x to the power of n plus an minus 1 x to the power of n minus 1 and so on, the plus signs, or in other cases the minus signs, can just be computed and taken out separately. So we compute the integral of an to the power of xn separately, and then add another integral of an minus 1 of x to the power of n minus 1, and continue doing this until the last term. These three are the most basic integration rules, so now that we know them, let's take a look at an example. For the first example, we're tasked with computing the integral of x raised to the power of 2 over 5. So here, step number 1, we would first add 1 to our power. So now x is going to be raised to the power of 2 over 5 plus 1, which in our case is going to be 7 over 2. And then we have to divide the entire thing by this new power, 7 over 2. And in the end, we have to attach a plus c, since there are a family of possible functions. Simplifying this answer, we get 2x to the power of 7 over 2 divided by 7 plus c. For the next example, we have a polynomial. We're asked to compute the integral of 4x cubed plus 3 minus 6x to the power of negative 3. So, according to the basic rules of integration, to be precise, the one about the polynomials, we can actually separate this integral into three different ones. So, for the first term, applying the power rule, we get 4 times x to the power of 3 plus 1, which is 4, and then we divide it by the new power, 4. Next up, we have the number 3. Now, if we are integrating a constant which does not have any x value attached to it, that simply means that its x has the power 0. We could rewrite this term as 3 times x to the power of 0, since we know anything to the power of 0 is simply 1. So this is the same thing. And then we can apply the power rule to 3x to the power of 0, meaning we get 3x to the power of 0 plus 1, which is the first power, and then divided by 1, both of which we don't write and can simply be omitted. And finally, we have the last term. So for the negative powers, we can also apply the same power rule. what we get is going to be 6x to the power of negative 3 plus 1, which we would get negative 2, and then we divide it by negative 2. Now that we have applied the power rule to all three terms, it is time to do some simplification. Here, 4 and 4's cancel out. 3x is as simple as it can get. And of course, in the end, we have two minus signs here, which means that they also cancel out into a plus. 2 and 6 can also be simplified to just 3 on top. So this means that the integral, or the antiderivative function we're going to get, is x to the power of 4 plus 3x and plus 3x to the power of negative 2. All of this isn't really so complicated. So now let's move on to the next part of basic integration rules, and that will involve trigonometry. From part 10 of this series, when exploring derivatives, we know the following three things. We know these three basic derivatives. The derivative of the sine function is going to be cosine. The derivative of the cosine is going to be the negative sine. And finally, the derivative of the tangent is going to be secant squared. So now, if we know that integrals are used to find the antiderivative or simply reverse the derivative action, that means the derivative of the cosine function is going to be the sine function. But of course, we do have to add a plus c at the end. Next up, the integral of the sine. We know, technically, that the integral of the negative sign is going to be the original cosine. However, here we have the positive sign, so that means the negative sign goes to the other side, and here we get negative cosine x plus c. And finally, the integral of the secant squared, we would simply get the tangent function, and once again, plus c at the end. Now, if you remember something from derivatives, you may remember this line. This line here, the arrows show the direction of the derivatives. Sine derivative is going to be cosine, cosine derivative is going to be negative sine, and negative sine derivatives is going to be negative cosine. And finally, when you do this derivative again, you're going to go back all the way to sine, and this cycle is just going to repeat itself. However, this is going to be from left to right. For the integrals, on the other hand, we have quite the opposite. When you do the integral of sine, you get negative cosine. And when you do the integral of negative cosine, you get negative sine, and then further cosine, back again to sine, and the cycle is going to repeat itself. Just like with the derivatives, however, in the opposite direction from right to left. So now that we know this, let's take a look at two examples involving trig. I do have to warn you beforehand that in order to successfully compute certain integrals of trigonometric functions, you will need to know the trigonometric properties very, very well. These include all of the identities, all the double angle identities, and the Pythagorean identities, and so on. Because those things are meant to make your function simpler to integrate. Now, back to the example, we have the integral of x plus sine x. So first, I have to apply the power rule to x. So x is originally raised to the power of 1. When I do the integral, it's going to be x raised to the power of 1 plus 1, which is 2, and divided by that power over 2. Next, I have the integral of sine, which we already stated before is negative cosine. So I write minus cosine x. And of course, never forget, in the end, we have to add a plus c. Next, for another example, let's take a look at something more difficult. We have the integral of x squared minus tan squared x. So we already know for the front part here, I'm going to use the power rule. What I get is going to be x to the power of 3 over 3. However, if you're tempted to use the power rule again for the tangent in order to get tangent to the power of 3x over 3, you would be completely wrong. This is not the way we do it. First, from the tangent squared, let's remember an identity, a trigonometric identity that says tangent square x plus 1 is actually equal to secant squared x. So this basically just means tangent squared x is equal to secant squared minus x. So here, for now, I'm going to write minus the integral of secant squared x minus 1 dx. What I did was simply rewrite tan in terms of secant and a constant, the integrals of which I already know. So here the answer we're going to get again x to the power of 3 over 3, then further minus. The integral of secant squared, as we have already stated before, is going to be the tangent x. And then we have two minuses. So minus and minus, it goes to plus the integral of 1, which is simply x. And of course, at the end, we must add a plus c. So this here concludes the basic of the rules of integration. However, to end the video, I would like to actually solve an example, which has something to do with finding that plus c at the end that's probably been bothering you for a very long time. Here, we are given the following conditions. The second derivative of a function is given by 2 plus 3 cosine x. And then the first derivative and the original f function are not provided. However, a set of coordinates are given. When you plug in 0 into the first derivative, you get the corresponding 4. And when you plug in 0 into the original f of x, what you would get is 5. And we're tasked with finding the original f of x expression. However, we're given the f second derivative. So this means when we do the integral once, we're going to get the first derivative, and then we're going to have to do the integral once again in order to find the final function. So first, let's begin with computing the integral of 2 plus 3 cosine x dx. Here, using the power rule, we would get 2x plus 3, and the integral of cosine, you would get the sine function, and at the end, plus c. Here, what we got is simply the first derivative, the expression for the first derivative. However, one thing unclear once again is this plus c at the end. So here, the conditions that the exercise gave us about the points 0 and 4 come into play. When we plug in 0 into this expression, we get an answer 4. So that means 2 times 0 plus 3 sine of 0 plus c is going to be equal to 4. Now 2 times 0 is simply 0. Sine of 0 is actually, once again, just 0, and times 3, it is still going to be 0. And plus c is going to be 4. So this just tells us that c equals to 4. So that means our renewed first derivative expression is going to be 2x plus 3 sine of x, and at the end, plus 4. However, this is not all, because we're supposed to find the original f. It means we have to do another integral, this time of the f first derivative function. Here, we can continue applying the power rule. For the first term, we get 2x squared over 2. Then, the integral of sine is negative cosine. So what we get is minus cosine x, and then plus 4. 4 is a constant, so integrating it, we would get 4x. And of course, never forget, in the end, again, we have the plus c. Of course, in the front, 2 and 2's will cancel out, so we would simply get x squared. Once again, just like with the first derivative, in order to find that c, we have to use the initial conditions given in the exercise, where it says if I plug in 0 into this expression, I would get 5. So that means 0 squared minus 3 times cosine of 0 plus 4 times 0 plus c is going to be equal to 5. Here, 0 squared is 0, cosine of 0 is actually 1, and of course, 4 times 0 is just 0, and plus c at the end equals to 5. So here we get negative 3 times 1, so negative 3 plus c is going to be equal to 5. And what that does tell us? That tells us that c is equal to 8. So the final answer that we get after evaluating everything, the original f of x expression is going to be x squared minus 3 cosine x plus 4x and plus 8. Now you can see there are no plus c's at the end, just a constant that we calculated because the exercise gave enough conditions to solve it. All right, so this is it for today. I hope this was helpful. In the next video, we will look at how to integrate some basic composite functions, just like with the derivatives, how we did the chain rule. The integrals also have its own chain rule, but it's a bit more different. So you will see in the next video. So I definitely hope to see you there, and have a nice day. Bye.